All right, and we're live. So I'm going to really quickly run us through all of our standard deviation z-score stuff and get through hypothesis testing today. We'll have a chance to do some hypothesis testing problems, and then we'll break for homework. So before I get into standard deviation, usually when we talk about a distribution, so something like this, we usually talk in terms of shape, center, and spread. So for shape, for this particular shape, I've got a bell curve. For measures of center, we usually use mean, median, or mode. And for measures of spread, we could use range, IQR, or variance or standard deviation. Okay, so let me go through all of these really quick. Starting with Aileen. Aileen, what does mean mean? What is the mean? Mean is an average, if that helps. So how can you get the average? If I wanted to get the average of all of these numbers in our data set right now, what would I have to do?
Add them up and divide.
Okay, so the sum of the values and then divide by what?
The number of values.
Divide by the number of values. Perfect. Okay, Jana, how would I find the median of this data set? Okay, median means middlemost, you're right. How would you find it?
Like separate the lower half to the upper half and then the middle term.
Okay, so take out the lower half of values and then the upper half of values. So that'd be something like this. I'm going to cancel out one value from the top and the bottom and just keep doing that again and again and again until we end up with our middlemost value. Okay, what if I end up with an even number of values?
Add and divide.
Add and divide by... Divide by how much?
2.
Divide by 2, perfect. So if you end up with an even number of values, then I would take the average. So the median of this set is 5. Okay, and then what about mode? Niall. What is the mode and how can you find it? And you can type if you don't have a microphone. I've got you on Zoom for the moment. Okay, so while Niall's typing, I've got Kelly next. Um, Kelly, I'm gonna have you do both range and IQR. Um, Kelly, how can I find the range?
The largest number minus the smallest number. So 4
Perfect. Largest number minus smallest number. And then
mm,
what about IQR?
is um the third quartile minus the first quartile, something like that. I forgot.
Okay, that's perfect. Let's go through and we'll see if we can do that really quick. So just gonna rewrite these x's. Okay, how can I find Q1?
It's the uh
Give you a hint
hmm,
with a line there.
is mm, is it the um median of the first half?
Yes. Median of the first half. Um, okay, so here's my first half of our data set. And we'll take the median the same way we did last time. So taking one from the bottom and one from the top until we get to the middle, which is here, is Q1 at 4. Okay, and then we'll do the same thing for the other half. So here's our top half. Gives us Q3. Your median is Q2, so that's the 50% mark, or 2 times 25%, which is a quarter. Q3 is your 75% mark, 3 times 25%. Q1 is your 25% mark, 1 times 25%. Your IQR is the range of values that include the middle 50% of all values, which means the 75% mark minus the 25% mark would be the middle 50% of all values. Okay. Okay, I'm going to skip down to Sarah. So I think Niall was answering the IQR question. So for Sarah, how can I find the mode? Or what does the mode mean? Sarah, can you give me a definition for mode? Or how you would find it?
Uh, Mode is the number that occurs the most.
Perfect. Okay. So these are all of your SAT values. Got an echo. Okay. If these are all of your SAT values, the last one we need is our standard deviation. Um, so our standard deviation tries to solve a problem of creating a number that tells us how much change there is in a distribution. So originally we tried to just add up differences from the mean. So if this is your average and we've got units that are 4 units above average and units that are 4 units below average, we can add them all together. Unfortunately, our negatives will cancel out our positives. We'll end up close to 0. So the next thing we tried was absolute values. All of these values that are 4 units above the mean are the same distance from the mean as these units that are 4 units below the mean. Unfortunately, while this looks good at first, it does mean that these two distributions, 4, 4, -4, -4 from the mean, and 7, 1, -6, -2 from the mean, end up having the same value for their average distance from the mean. Which, looking at these two distributions, I think you guys would agree with me that one of them has more change. Aileen, which of these distributions do you think has more change? The top or the bottom?
Bottom.
The bottom, you're right. So this has more change from the mean. So what we did was we squared our differences instead. So that gets rid of our problem where negatives cancel out with positives. So if we square a negative, that becomes a positive. And it weighs values that are further away from the mean a little bit more. So the more change that you have, the larger your number should be. So if I do that now, I get my average squared difference from the mean. So I've got 4 units above the mean, 4 units above the mean, 4 units below the mean, 4 units below the mean. All of these are 4 units away from the mean. If I square that, that's all 64. But for my bottom one, 7 units away from the mean will give me 49 units instead of just 16 for one individual one of these units. So the further you are away from the mean, the more it weighs. The closer you are to the mean, 1, only give me a weight of 1. Okay, so that with that, if we square all of our differences from the mean and then take our average squared difference from the mean, I end up with a number that is much larger for this bottom value that has more change, which is exactly what we were looking for. Because this number is huge though, if I just take my average squared difference from the mean, this would be 90 divided by 4, is much bigger than what we could graph related to our other numbers. I'm going to take the square root again. So that brings us back down since we squared all of these differences from the mean. If I take the square root again, that'll bring us back down to something that we can graph. So now my difference is only 4.74, which is something I can graph on this data set. Okay, so that's standard deviation. Standard deviation is the sum of the squared difference from the mean divided by the number of numbers, and then we take the square root of that. Okay, any questions on what standard deviation is or why we have it? Okay. So the standard deviation is a really good measure of spread, but it also allows us to compare things that are completely different. I'm going to check and make sure this isn't one of you guys. Nope. Okay. Okay. So we started working with z-scores by comparing different sports. So let me explain what we're doing really quick. One of the cool things about standard deviation is that if you have a bell curve, once you know what one standard deviation is, one standard deviation above or below the mean will always enclose the same percent of all values. We can count how many standard deviations you have above or below the mean by taking the difference of a score minus your average, so that's how far away you are in your units from the mean, and then dividing by how much units one standard deviation is to tell you how many standard deviations you are above or below the mean, which we call a z-score. And we can use those z-scores to compare completely different things. So when we started talking about this, I gave you this example where I had my sport in middle school and my brother's sport in middle school. So that's downhill slalom versus long jump. But looking at Olympic medal results, if I wanted to see which one was more impressive, we could use z-scores to compare them. So what I would do is I would take the gold medalist score, 87.93, subtract the average, 94.27, and then divide by how much one standard deviation is, 5.28. This is giving me an idea of how extreme was this gold medalist score compared to other people who are in that person's sport. So in this case, how much further away from average was the gold medalist score compared to other people who are skiers? And we do the same thing for the long jumpers. And if we do, we get two different z-scores. So our downhill slalom was 1.2 standard deviations below average, which is good because this is a race, so you want your time to be low, versus a long jump, which was 2.7 standard deviations above average, which again is good because we want our distance in this case to be long. So completely different sports. They're measured in different ways, and one we want our score to be low. Low is better. And one we want our score to be high. High is better. But by comparing our gold medalist results to everyone within their own sport, we can get a comparison between these two sports to see which gold medalist is more impressive compared to other people within their sport. So in this case, the gold medalist for the long jump is more impressive compared to other long jumpers than the downhill slalom is compared to other downhill slalomers. Any questions on what we did with our z-score here for comparisons? Okay. So showing what we just did graphically, if this is average, once we've standardized to a bell curve, our slalomists were 1.2 z-scores, 1.2 standard deviations below average, where our long jumpers were 2.7 standard deviations above average. Okay. We also talked about using a z-score table, and if you don't have a graphing calculator at home, then I'm going to be providing you with the z-score table that you guys can use for your homework tonight. To use your z-score table, first you go down your tenths column, and then match that to a hundredths digit. So if I want to find a z-score of 1.96, and I want to know how much area that would enclose, I'll go to the hundredths column, or go to the tenths column where I see 1.9, and then follow that to the hundredths column where I see 0.06 and match that. So a row of 1.9, a column of 0.06 gives me 1.96 for my z-score, encloses 97.5% of all values. With a z-score of 1.96, standard deviations above average. Okay. If I wanted to do this in a calculator, we can do it with our normal CDF function. Our normal CDF function takes two arguments, a z-score 1 and a z-score 2. And it will tell you the area between those two z-scores. Does anyone remember if I wanted to do my z-score from the end of the graph, so that's negative infinity, until 1.96, what would I have to type?
Negative 1 E99.
Perfect, to 1.96. So this is the smallest value our calculator can hold without giving an overflow error. Its scientific notations, this is actually negative 1 times 10 to the 99th power, which is just a super large negative number. So let me pull up a graphing calculator and we'll do that really quick. So in your graphing calculator, you would type second distribution, and then scroll down to normal CDF, negative 1 e to the 99, and then our second z-score of 1.96, and that tells us it includes 97.5% of all values. Okay, so that brings us to hypothesis testing. So when we are hypothesis testing, what we're looking for is a significant difference. So in your science classes up until this point, if you, to use the same example I'm going to see in a second, wanted to test to see whether a fertilizer makes plants grow taller or not, you would have had a control group. So that's a group of plants that do not have any fertilizer, and an experimental group, a group of plants that do have fertilizer. So maybe you would have given the plants with fertilizer their fertilizer for 20 days and then checked to see the height of the plants, and then given the control group no fertilizer, and after 20 days checked to see the height of the plants. And if the experimental group ended up with taller plants, you would have said that the fertilizer works. The problem with that is some plants naturally grow taller than others. So that difference might not have been because of the fertilizer, it might just have been random chance. So what we're going to try to prove is that the probability of getting a random plant inside your control group to grow as tall as your experimental group is small enough that the difference is not because of random chance, but the difference is because of the fertilizer. So because of some other outside condition that's different between the two. And as long as you've controlled your variables, that should be your experimental variable. Any questions on what we're trying to do? Okay. So with that, there's 3 different types of testing that we can do. We can either do a two-tailed test, where we're just looking for any difference. So our fertilizer, when we give it to the plants, could cause them to grow shorter, or it could cause them to grow taller. In that case, this would be a two-tailed test, because it could be larger or smaller than what we are expecting. If nothing happens, in math we have 2 hypotheses, so if nothing happens, that would be our null hypothesis. Null literally means nothing. If nothing happens in this case, the experimental group and the control group would end up with the same result. If they both had the same height, our chi, that's our experimental group, ends up with the same height as our mu, which is our control group. Then we can say nothing happened. The fertilizer didn't do anything. Alternatively, if our experimental group is significantly different, so either less than or greater than average, then we could say that there is a difference. If I wanted to do a one-tailed test instead, so let's say this is our bell curve, I want to test and see if our fertilizer grows larger than average, then the fertilizer would not be working. Fertilizer would not be working in this case on this one. If our experimental group is smaller than or equal to average, it would be working if it made our plants grow taller than average, and there would only be one tail for that. Okay, similarly, there'd only be one tail if I'm looking for our results to be less than average. If I want our results to be less than average, my null hypothesis would be that we are larger than or smaller than average. And my alternative hypothesis would be what happens if our plants are less than average. Any questions on null or our alternative hypothesis?
No.
Okay. So here's our fertilizer with plants again. In this case, I want our plants to grow faster than plants without fertilizer if I give them the fertilizer. So that means my experimental group, or chi, will be our plants that have fertilizer. In this case, what is x and what is mu? I'm down to Jenna. So Jenna, what is x or chi?
72 hours.
Okay, so with fertilizer, they grew an average of 72 hours. What is mu?
78.5 hours.
Okay, 78.5 hours. That's our expected value, um, or mean. Then we have a standard deviation, which is my sigma, of 4 hours. If I want to be 95% confident in our results, then what should our alpha be? Kelly?
0.05.
0.05. Perfect. Alpha is the probability that you are willing to accept that we are wrong. So in this case, if I want my plants to grow faster without fertilizer, that means they would have significantly less time to grow than average. If you are willing to accept a 0.05, so that's a 5% chance that we are wrong, then I would want my plants in my experimental group to fall somewhere within the bottom 5% of all random values of plants without fertilizer. And if it falls within that bottom 5%, then we can be at least 95% confident that the difference is not just random chance. Okay, so in this case, null hypothesis is that chi is greater than or equal to mu, which means they'd be growing slower, which takes more time. Alternatively, chi will be less than mu, which means we'll be growing faster or will take less time to grow. Any questions on anything from the setup? Okay.
No.
So we can set this up then and get a z-score. So that's how many standard deviations below average is our sample. So this is our sample average minus our expected value divided by the standard deviation. Now I am lying a little bit here, which you'll see if you go into a statistics class, in that normally we don't know the perfect standard deviation for all plants of any species. So if you keep going to a AP statistics next year, you'll see a slightly different number for your sigma. You'll see this. As your z-score, where this bottom part is what we call a standard error, and that's because in real life we usually don't know the perfect standard deviation. So we intentionally cause our z-score to be a little bit wrong. To make it harder to prove a significant difference if we don't know the standard deviation of the entire population of what we're studying, which in this case we wouldn't know in real life. But since I'm giving that to you, our actual standard deviation for the population of all plants of this species is 4 hours. Okay, so we get our z-score. I've got our z-score of negative 1.625. And then I can use that to get our probability that a plant with that z-score or less of a z-score of negative 1.625 standard deviations below average would happen by random chance. So this is the probability that you would randomly get a plant that grows faster than our sample size. Okay, I can do that in our calculator. So again, I've got a second distribution normal CDF function going from negative infinity, negative 1 e to the 99, to our z-score, in this case negative 1.625. Gives us our p-value of 0.052. Which means there is a random chance of 5.2% that you would get a plant that grows this fast without fertilizer. Okay, what's our conclusion? Sarah? We just said there's a 5.2% chance that a plant without fertilizer would be faster than our sample. So can we be 95% confident that our sample is different or not?
Yes.
Okay, in order to be 95% confident, then I would need this area to be less than 5%. Unfortunately, right now we are more than 5%. We're 5.2% confident. That might have been my handwriting there that messed you up, but this is, sorry, this is 0.052. So this is 5.2% that we have within this area. So if that's true, then we don't have enough evidence to be 95% confident in our result. Okay, I'm going to break out of this. And we'll try at least one more example. Oops. Okay, I know we've done this one before, but we've got our average Japanese girl born at 3 kilograms, the standard deviation of 0.4 kilograms, and Aiko, who was born with a mass of 3.67 kilograms. I want to know if Aiko was unusually massive for a Japanese girl when she was born. Aileen, what is my null hypothesis and alternative hypothesis?
It's the hypothesis less than.
Okay, our sample should be less than or
Less than.
okay, so this should be less than or equal to what?
The standard deviation.
Not standard deviation.
Mu.
Mu. Okay, and then what's the alternative?
Zero 0.05.
Okay, 0.05 is what our alpha, what we're willing to accept. What's our alternative hypothesis?
X is greater than mu.
Perfect. So we can prove something. We want to prove that Aiko's mass in kilograms when she was born was larger than the average. So that's our alternative. Our null hypothesis, if we cannot prove anything, null means nothing, would be Aiko is less than or equal to the average Japanese girl in kilograms. Okay, Jana, what is mu, what is chi, and what is sigma?
Mu is 3 kilograms.
Okay,
For chi, 3.67 kilograms.
Okay, and for sigma?
Sigma 0.4 kilograms.
Perfect. Okay, and then we weren't given a confidence level, so I'm going to assume that our confidence level is 95%, which means we are willing to accept a 5% chance that we are wrong. Okay, over to Kelly. Kelly, how can I get our z-score?
3.67 minus 3 over 0.4.
Okay, so that's 3.67 minus 3 over 0.4. Should give us our standard deviation
Yeah.
of 1.675. What are our units?
Kilogram?
Not kilograms in this case. Z-scores always measure what?
Um, I, I don't know.
Okay, I'm going to open to anyone. The units for every z-score, no matter what the problem is, are always the same. What do z-scores actually measure?
Is sigma?
Right. So I'm going to write in words, though. This is standard deviations. So in this case, we are 1.675 standard deviations above average. Okay, so then I need a p-value, which brings us to Sarah. Sarah, how can we get the p-value?
NCPR 1.1.675.
Okay, where are we starting from though? Sorry. You're actually right. 1.675. Okay, so we're going up for this one. 1.675 up to what?
1 on the east side.
Okay,
9.
perfect. So what we're trying to write is positive infinity, which we'll type in the calculator is 1 e to the 99. Okay, second distribution normal CDF, so that's 1.675 to infinity. Gives us a p-value of 0.0469. Okay. Aileen, back to you. Is the p-value less than or greater than alpha?
Less than.
Okay, p-value is less than alpha, so how confident can we be in our result?
95.3%.
Okay, a little bit more than 95.3%, perfect. So what would our conclusion be?
We have enough evidence to prove that ICO was unusually massive.
Okay, we're really close. How confident can you be?
95%.
Okay, we can be 95. I'll say more than 95. We can be more than 95% confident that what?
Aiko was unusually massive for a Japanese baby.
Perfect. All right. Any questions on what we did for our hypothesis test?
No.
Okay, I'm gonna break here then. Um, if you guys still have questions, you can stick around. If not, we are going to finish the rest of the probability retest that you did not do. So that's page 4, 5, and 6, which are all hypothesis testing or z-score stuff. If you need a z-score table, the last page of the probability test has your z-score table for you in case you don't have a graphing calculator. All right, so I'm going to take this up on Friday at midnight. Thank you guys so much for coming, and I will see you again on Friday.
Bye.
Bye.